Hello, dear students. Welcome again in the class of nuclear physics. So, in the previous lecture, we have discussed about the beta transitions, and we have discussed in detail about the selection rules of beta decay, and we have discussed with some numerical problems about the allowed and forbidden transitions. So, in this today's lecture, we will do the derivation of Fermi theory of beta decay, and we will derive the expression of the transition probability and how the rate of the transition we can derive, and which tells us about whether the transition it can be allowed or forbidden transition. So let us start our lecture. So, after the discovery of polyneutrino hypothesis in the early 1930s, so Enrico Fermi in 1934 he derived about the theory of this Fermi allowed beta decay, and this is generally known as the Fermi theory of beta decay. Now, according to Fermi, the rate of transition for an initial state to final state it is generally given by, so this W it is generally known as the rate of transition. So it 2 pi over h bar, so HIF square into density of states, which is dependent upon the energy of the emitted particles. So this H, which depend upon the initial and final state, it is generally known as the matrix element, and this is for the perturbing interaction which is causing the transition from this initial to final state, and we generally write this matrix element which is dependent upon the initial and final wave function. H is the total Hamiltonian energy interaction function, so psi I, which is the initial wave function, into d tau. So, in order to find out the transition probability, we need to derive these two expressions. We need to find out this matrix element, and we need to find out the density of states for the type of interaction which we are studying. So, this matrix element it is dependent upon this function h, which the Fermi it is has considered. Generally it is known as the electron neutrino field. So let us say this is our equation number 1, this is equation number 2. Now equation 1 can be applied to the case of emission of electromagnetic radiation from an atomic or nuclear system. So this Enrico Fermi he took the analogy of the electromagnetic interaction. So it is similar like when an electron which is jumped from initial to final state or final to initial state, ground state, then it is emitting some sort of photons, and so he take the analogy of these radiative transition and the perturbation which is causing this radiative transition is due to the electromagnetic field, and where the quantum manifestation or the particle which is emitting in this atomic or nuclear radiative transition, that is a photon. So we all know about this emission of photons from this electromagnetic field when this wave it is moved from one state to another state. So its form is known. So the quantum particle which is coming is a photon. However, in the case of this beta emission, the nature of perturbation it is not known, and he considered that there is some sort of electron neutrino field which is present within the nucleus, and due to the exchange of these neutrino and electron, and the quantum manifestation is the pair of these two particles. So the beta particle which is coming, and along with that the antiparticle, that is the antineutrino, which is also coming out along with this beta decay according to this neutrino hypothesis. And he considered that there is some sort of electron neutrino field which is being present, and he derived his theory based on this electron neutrino field. So according to Fermi, so if we write down the beta decay equation transition, so suppose this is our parent nucleus, and this is Y is our daughter nucleus, and when there is a emission of a beta particle, then the atomic number it is increased by 1, and with the emission of a positron, the atomic number it is decreased by 1. So this electron and neutrino particle it is being emitted. So this electron, and along with that the particle which is coming out is the antineutrino. So this is for the beta minus decay, and for the positron emission the particle which is coming out is the neutrino particle. This is for the beta plus decay. So depending upon what type of transition, so we can use this equation. So if we can use this equation, so if I write this equation something like, so when I move this particle, suppose this parent nucleus it is absorbing some sort of this particle, and this particle, so we can write this equation plus electron. So using this equation number 3, so we can derive the initial and final states of the parent and daughter nuclei, and from that we can find out the wave function, and from that we can find out the value of this matrix element. So in this equation number 3 you can see that the initial state wave function, so now I can derive or write the initial state wave function as psi I. So it should consist of the initial state nuclear wave function, so that is ui, and the leptonic wave function that is due to this neutrino particle. So similarly the final state wave function, so that is on the right hand side of the equation number 3, so it is considered as the final state wave function uf of the nuclear wave function, so the particle that is generally the daughter nucleus, and the uf particle with the leptonic wave function of the beta particles. So these electron, positron, neutron, neutrino and antineutrino, so they are generally known as the lepton particles, and we generally derive these as the leptonic wave functions. Leptonic wave function. So these two. So there is another difficulty for the beta decay. The exact form of this nuclear wave function it is not known. So we use the simplest form of this electron neutrino field. So where the value of this H it is invariant. So the metric element we can write down as summation of n, which varies from 1 to infinity, integration of frn. So where f is the undefined parameter which depends upon the leptonic wave function of this beta or anti-neutrino particle multiplied by the final state wave function operator on into ui. So we have break down this psi I and psi f into the separate wave functions of this is the wave function of parent nucleus, this is for the daughter nucleus, this is the leptonic wave function for this neutrino, and this is for the beta particle. So this function Frn, it is the quantity which depends upon the wave function of phi b and phi nu of the particles of the nth nucleon, so which is undergoing the beta transformation. So here this operator On, it is generally known as the polar vector, so which is connected with this beta decay for the nth nucleons. So it is also generally known as the antisymmetric tensor or the pseudoscalar vector. So if I write the value of this function Frn, so this equation becomes G integration of UF star phi b star, so this is beta, phi nu operator On into Ui into 2. So this G, it is again the constant whose value depends upon the strength of the nuclear interaction, and this G, it plays the same role as the electronic charge E, which plays for the radiative or the electromagnetic transition. So let us say this is equation number 4. So for we need to find out these wave function for this electron and this antineutrino. So we can write these wave function as phi b, which is for this electron or positron wave function, 1 over under root omega exponential of I into kb dot rb. So similarly the wave function for this neutrino or antineutrino, which is 1 over under root of omega exponential of I k nu into r nu. So since neutrino or antineutrino, it is a chargeless particle, so its wave function we can generally consider as the planar wave function, which is justified. But this beta particle wave function, so it is a nonlinear wave function due to the Coulomb interaction, so which is occurring between this beta particle and the nucleon, so like the proton. So however, for the first order of approximation, it does not make any difference and we can neglect this Coulomb interaction, but in our next article we will also introduce the Coulomb correction. So by considering the Coulomb charge for the wave function, and we will derive that derivation as well. So if the particle, it is having some finite momentum, and suppose it is moving with energy of 1 mega electron volt, and from that we can find out the momentum, which is equal to E over C. So this we can write down in terms of 1.6 into 10 raised to power minus 19, so mega electron volt, so it will be 10 raised to power minus 13. So it is moving with the speed of light, so the momentum comes out to be 5.3 into 10 raised to power minus 22, and from this momentum, using the de Broglie hypothesis, we can find out the wavelength, for this wave. So putting these values, so it comes out to be 0.2 into 10 is to power minus 12 meter. And this k, it is generally representing the wave vector, and this r, that is the difference of these particles, the radial interaction rb. So putting the value of this, from this we can find out the wave vector, which is equal to 1 over lambda, so which comes out to be 5 into 10 is to power 12 meter inverse. So from this we can find out if the radius of this particle in the nuclear interaction, that is of the order of 5 femtometer, so that is of the order of 5 into 10 is to power minus 15 meter. And from that we can find out the value of k into r, so which comes out to be 0.0025. and you can see that this value, it is very less as compared to 1. So putting the value of this kr, or expanding our equation, these two equations, so if I write these equation as equation A, so applying these Taylor expansion, we can write down this beta particle wave function, which is 1 over omega 1 plus I kb dot rb plus I kb dot r beta square over 2 factorial, so and so. So this becomes a very small function, because the value of this kr, which is very less, and we generally neglect these values. So the value of this beta wave function, which is 1 over under root of omega. So similarly, so for this planar wave solution, we can write down this just a minute. So we can write down this neutrino wave function, that is almost similar, which is of the order of 1 over under root of omega. So putting the value of this beta wave function and neutrino wave function, so our for the allowed transition, the initial and final state wave function will be equal to, so psi I, which is equal to ui into phi nu, and the final state wave function psi f, that is equal to uf into phi b. So putting the values, so this equation becomes ui over under root of omega, and psi f, that becomes uf over under root of omega. So putting the value of this psi f and psi I in the matrix element equation, so our matrix element HIF, it becomes G over omega, so under root of omega and under root of omega, so this becomes omega. So this is for the confined normalized volume, where omega, that is generally known as the normalized volume. So it comes outside, so within the bracket, so uf star operator ui into d tau. So this we can write down as this whole integration term, so this we can generally written as the MIF. So this MIF is the nuclear part of this matrix element, excluding the strength G and the normalized volume omega. So this is our matrix element, excluding the value of G and omega. So this MIF we can generally write down as integration of UF UI into d tau. So we have find out this total matrix element, and the second we need to find out the density of states. So let us calculate density of states, because in order to find this total transition probability we need to find these two values. The matrix element we have find out. Now we need to find the density of states. So the number of states of the neutrino in the momentum range nu to some slightly perturbed new momentum, that is p nu plus dp nu. So so the number of these states for the neutrino we can write down as 4 pi p nu square into dp nu into omega over h cube. So similarly for the beta particle we can write down the number of states delta nb, which is equal to 4 pi pb square into dpb into omega over h cube. So the total number of states available for this beta and neutrino, so in the above momentum range within this confined volume omega, so this total number of states we can write down as dn, which is the density of states for beta particle multiplied by the density of states for this neutrino. So this putting the value of this delta nb and delta n nu, so this equation becomes 6 pi square omega square into h raised to power 6 pb square p nu square delta pb into delta p nu. So this dn it becomes 16 pi square omega square. So this we can write down as 2 pi into h bar raised to power 6 pb square p nu square into delta pb into delta p nu. So in order to get the density, so we divide this by the energy interval. So for this delta EB for the electron, so the density of states, so that is equal to delta N over delta EB. So since we are finding out the density of states for the beta particle, so we divide it with the energy of this beta particle. So EB plus E nu, so EB is the energy of this beta particle, E nu that is the energy of this antineutrino, and let us consider EM, that is the total energy. So the total energy which is being shared among these two particles, so that's why the spectrum of beta particle it is generally considered as the continuous spectrum. So the total energy it is always constant. So taking the derivative of this delta EB plus delta E nu, so the derivative of a constant it is equal to 0. So so we need to find out this value of dPb and dP nu. So E, we can see that the energy of this antineutrino which is equal to C into P nu. So this we can write down as the total energy which is EM minus of EB, and putting the value of this from this we can find out the value of the momentum of I will write out here. So the momentum of antineutrino, which is equal to Em minus of E beta over C. So similarly, we can find out the momentum of this beta particle. So that I will write out here. So delta of E beta from this equation, so that is equal to minus of delta E nu. So this we can write down as minus C into delta of P nu. Now putting the value of this P nu dEb in this equation, so this density of states, this becomes 16 pi square omega square over 2 pi h bar raised to power 6 pb square p nu square dpb into dp nu over c dp nu. So this dp nu and dp nu get cancelled. So all the values we have converted in terms of the dpb, that is the momentum of this beta particle. So density of states, so this becomes, so when we open this 2 pi raised to power 6, so it get cancelled with this 16 pi square. So we are left with this omega square over 4 pi raised to power 4 h bar the power 6 into c pb square p nu square into dpb. So putting the value of this momentum of antineutrino, so this equation becomes omega square over 4 pi raised to power 4 h bar the power 6 into c dp square em minus eb square into dpb. So this is the value of the density of states for the emitted beta particle. So putting the value of this matrix element HIF and the density of states, our total transition probability, that is the rate of transition for the allowed beta transition. So this we have written, that is equal to 2 pi over h g square over omega square into MIF square, that is the matrix element, into density of states. So this equation becomes 2 pi over h g square over omega square MIF square. So putting the value of this density of states, so that is 4 pi raised to power 4 h bar 6 into c. So here I would like to add, so since the value of this p nu square, so this is divided by c square. So this is c square and c, so in the denominator we have a c cube value. So this is c cube. So pb square into em minus of e beta square into delta of p beta. So the transition probability, so this equation becomes g square over 2 pi cube into h bar 7 into c cube. So sum of they get cancelled. So when we combine these two values, we get this value into MIF square into PB square EM minus of E beta square into dP beta. So this is very important equation, so which is generally known as the rate of transition for this allowed beta decay. So which tells us about the what type of reaction it can be so which define the rate of transition. So whether it is a allowed transition or forbidden transition, so that is generally defined with this transition probability, and this value of MIF and the value of this momentum of the particle, which generally tells us about the comparative half-life, and that we will discuss in our next lecture. So this expression, you will see that it is independent of the normalized volume omega. So this is a very important expression, and many times this question it has been asked in the final year examinations. So this is very important. So in our next lecture we will do this transition probability expression by introducing the Coulomb correction, because in this we have taken the case of the beta transition for the planar wave, but due to the Coulomb charge it is present, so it is no longer a planar wave solution, it is a non-linear wave solution, and we introduce this Coulomb correction and find out this Fermi function, and from that we will drive out the new expression of transition probability for this relativistic Coulomb correction. And after that we will discuss about some shape of the spectrum, why it is a continuous, and some small topics about this Curie plot and what is the mass of the neutrino. So till then, goodbye, see you in the next lecture.